So part of Unit 2 is talking about bonding and what types of bonds compounds have. So the first type is ionic bonding. It occurs between atoms with very different electronegativities. Usually that's going to be between a metal and a nonmetal. One atom is going to give up electron and become positive, and the other atom gains electrons and becomes negative. Substances that undergo ionic bonding are usually solids at room temperature because they have very strong attractions between the ions. They do not conduct electricity at room temp as solids because the electrons are localized around each atom and they're not free to move. So does not conduct as a solid. Liquids and aqueous solutions can conduct electricity because their ions are free to move at that point to transfer that charge. And they have high melting and high boiling points generally. Metallic bonds occur in pure metals and alloys. So we have pure metals such as iron and silver, and alloys such as steel and bronze. We'll be talking more about alloys later in this unit. This is a picture of what metallic bonding would look like. We have our positive ions, and our electrons are delocalized, meaning they're free to move around. So electrons are delocalized. So we basically have this sea of electrons that are going between the cations. Metals are the only type that can conduct an electric current as a solid. They're going to be malleable and ductile. They're malleable because whenever you hit it with a hammer, you can move the cation and the electron. So unlike an ionic, where if you hit it, this positive may be right next to this positive, which would cause repulsion. With metallic, when you hit it, it doesn't really matter because the positive ions have the electrons that are free to move. Covalent bonds occurs when electrons are being shared between atoms. So this is going to be our nonmetals. So carbon dioxide, H2O, etc. Covalent compounds do not conduct electricity in any form. That's going to be the easiest way to tell if something is ionic, covalent, or metallic lab-wise is if I test the electrical conductivity as a solid and it conducts, it's metallic. If it didn't conduct as a solid, but I put it in water and it conducts, then it's ionic. And if it never conducts, then it's going to be covalent. They're going to have the lowest melting and boiling points generally because they have weak attractions between them, and they're generally insoluble in water. With covalent bonds, you need to understand polarity, which is when the electrons are not shared equally in a covalent bond. When we have polar molecules, they're going to exhibit a dipole moment, which is the greater the charge at the ends of the dipole, the greater the distance between the charges, the greater the dipole moment. In other words, the greater the electronegativity difference, the more polar it's going to be, the greater the dipole moment. And polar molecules have permanent dipoles. Go ahead and pause the video and figure out which of these bonds is increasing in polarity. Restart when you're done. To figure this out, you should have found the differences in electronegativity. It doesn't matter that there's 4 hydrogens. I'm looking at just the difference between 1C and 1H. So 2.5 minus 2.1 is a difference of 0.4. Silicon and chlorine has 3 minus 1.8 gives me 1.2. And 4 minus 2.5 is 1.5. So these are increasing in bond polarity. So the answer was A. Go ahead and pause the video and figure out which of these is an ionic bond. So if you said B, you're correct. And that's because rubidium and oxygen have the greatest electronegativity difference. They're the furthest away from each other on the periodic table. You have a metal and a nonmetal. A and C were the least likely to be ionic because there wasn't a metal there. So it's between B and D, and rubidium and oxygen are very far apart. They have a large electronegativity difference. We've talked about bond energy in Unit 6, But bond energy has to do with three things, or bond strength has to do with three things: size, polarity, and bond order. The smaller the size will generally result in stronger bonds. So previously we had said HCl versus HBr. We said HBr would generally be a weaker bond because chlorine is smaller, so the H and Cl can get closer together. Polarity, the more polar the bond, generally the weaker the bond. So Hi versus HF, Hi is not as polar as HF is, so HF is generally a weaker bond. We also said that HF, even though it is very polar and should be a weaker bond, fluorine is very small, and so that bond is actually pretty strong because fluorine is so tiny. So size and polarity do go hand in hand. You can't just make a blanket statement that because it's polar, it must have a stronger bond, or just because it's smaller, it must be a stronger bond. Bond order. Single bonds have bond orders of 1. They're going to be longer and weaker. Double bonds are bond orders of 2. Triple bonds are bond order of 3. We also have seen one of these charts before. So with bond energy, we have bond length, which is left to right. So the further to the right it is, the longer the bond length. The further to the left, the shorter the bond length. Notice that this one is too close. Therefore, we're going to have repulsions happening, and these are too far. So further to the right is too far, further to the left is too close. At the optimal separation, that's where we're going to find the bond length. So bond length, again, is left-right, or on the x-axis. The lower the valley is in the graph, the stronger the bond. So bond energy is going to go up-down. So this is how much energy is released. And if that's how much energy is released, then that's how much energy will have to be put into it to break the bond. So let's go and look at a couple of questions you could see. Go ahead and pause the video and try this one on your own. Restart when you're done. So we're talking about point 2. And at point 2, that is our maximum stability. And it's going to release 200 kilojoules. So that's why A is correct. So it's not minimum stability, it's going to be our max stability. Go ahead and pause the video and try this one. Restart when you're done. So here we're looking at point 1. And at point 1, that is very far to the left. It's very, very close together. So the repulsive forces are going to dominate. Go ahead and pause the video and try this one. So it's saying at point X, which of these is true? And that's the attractive and repulsive forces are balanced. So they're going to maintain an average internuclear distance of point X. Go ahead and pause the video and answer these two questions. Restart when you're done. So the longest bond length should be the one that's further to the right. So out of these two, this is my X, this is my Y. Y has a further bond length. So that's my longer bond length is Y. For most energy, I'm looking for the one that's further down. So this is X, this one is Y. X is further down. It's going to require more energy to break X. For your reason why, so X, because X releases more energy, so X would require the most energy to break. And here's our last one. Go ahead and pause the video and try this last one. Restart when you're done. So there is my valley, and so it has a bond length of about 75 picometers. So it's not about the force. We're looking left to right. So the second one. To figure out the strength of ionic bonds, though, we're going to look at size of ions and charge. First, we look at charge. The bigger the charge, the stronger the ionic bonds. Then we look at size. Smaller the ions, the stronger the bonds. You can read the paragraph below, but it's summarized in the orange section above. So first off, sodium chloride and sodium bromide are both ionic. And so it says, why is sodium chloride melting at a higher temperature? Well, they have the same charge, and I want small size and large charge. Since the charges are the same, I'm looking for whoever has the smaller size. Well, they both have sodium, and chlorine is smaller than bromide, so the answer is D. On this one, they're giving you the lattice energies. The more negative it is, the stronger it is. So this negative 922 would be the strongest ionic bond, because you're going to have to put in 922 kilojoules to break it. So go ahead and pause the video and figure out, of these four substances, which one has the strongest ionic bond and the weakest ionic bond. And then rank them. Once you've ranked them, then look at these lattice energies and match them up. Restart when you're done. So NAF, you should have said, was the smallest, because they all have the same charges, so we were looking at size. And since it's the smallest, it's the strongest. KBr is the largest, so it's the weakest. So I know that NAF must be 922, and my weakest was negative 688. That corresponds to W and Z. Then they both have chlorine, but sodium is smaller than chlorine. So this one is going to be the negative 769 and negative 718. It wants to know who X is, which is A. So for this one, we're going to draw solid lithium bromide. So go ahead and pause the video and draw 2 formula units of lithium bromide as a solid in this box. Restart when you're done. So for lithium bromide, you should have had them as separate ions. I drew mine with the lithium positive and bromide ion negative. You also could have said positive negative like that. And then I'm going to have my bromide above it, because I have to have negatives touching the positive. If I put a positive above it, then that would cause repulsion. And then a lithium over here. So that would be my 2 formula units. I could keep going up or to the side if I needed to draw more formula units. But it's got to be in a repeating unit, so that way my negatives don't touch and my positives don't touch, to minimize repulsions. So if I was to drop a lithium bromide in water, would it stay together like my solid to the left? Or would it break apart? If you said break apart, you are correct. So I should have a lithium ion, and I should have bromide ions in the container. So technically I would have 2 lithium and 2 bromide. But for simplicity's sake, we're just going to have 1 of each. So we're going to go in and include water. Let's add 4 molecules of water to this container. Restart when you have your water. So for your water, you needed to realize that hydrogen is slightly positive and oxygen is slightly negative. So the slightly negative oxygens should have been facing V positive lithium. And the positive hydrogens will be facing the negative bromine. That's going to keep the lithium and bromide from going back together. So let's look at the properties of metals and alloys. Go ahead and pause the video and look at this question. Restart when you're done. We've talked about it before. If it's a pure metal, then it's not going to be an ionic structure, so that's wrong. D is talking about cations and anions, but if it's a pure metal, then I wouldn't have cations and anions. Again, that's ionic. So the answer should have been C, because the pure metals have free floating electrons among those cations, which allow for the cations to glide past each other, like we saw earlier with the silver picture. Go ahead and pause the video and try this one. Restart when you're done. So aluminum is just Al, and so that's metallic bonding. So it doesn't have ionic, it doesn't have covalent, and it should be delocalized valence electrons. So the answer should have been D. On this one, it says which of these would best represent lithium. So go ahead and pause it and choose your answer. Well, lithium is Li with a positive charge. So it's going to be A. B shows lots of lithium ions, but there's no electrons. So how did lithium metal turn into lithium ion? Would need to be because its electrons are free to move. C shows twice the number of electrons because lithium is represented as a +2 charge, and in D it's a +3 charge. So that's why it's A. And now go ahead and try this last one. Restart when you're done. So A says the valence electron is tightly bound to the atom. So that's not right because, again, our electron's free to move. B says the valence electron is found in the interstitial holes, making it as an alloy. Well, alloys are a mixture of metals, and so that can't be right. Each silver has one valence electron that's free to move. This is why it can conduct electricity. Yes. And silver, very soluble, can't be right. Metals are not soluble. So now let's talk about alloys a little bit. We have two types of alloys, interstitial and substitutional. In an interstitial, we have smaller atoms that are going to fill the spaces between the atoms, such as steel. Compared to iron, carbon's very small, and so it's filling these little holes in the gaps. It doesn't fill all of them, but you can change the percentage of carbon by filling more holes or less holes. Having some of those holes filled are going to interfere with the electrical conductivity and the movement of the atoms forming the lattice. This restricted motion makes the alloy harder and stronger because, again, it's not able to move as much because some of the holes or gaps are filled in. So it's not as flexible. For substitutional alloys, we're going to replace some of the metals with some that are relatively the same size. So zinc and copper are roughly the same size. Notice that I don't have any in the middle. They're just replacing them in different spots. Because there are only slight differences between the size, the shape and the lattice of the more abundant atoms is distorted some, and the flow of electrons is disrupted. So we do have a lower heat and electrical conductivity, but it's still going to be harder and stronger due to the atoms not being able to slide past each other as easily. So generally your alloys are going to be harder and stronger than the original metal, and their properties are going to be different as well. Generally, they're going to have lower heat and electrical conductivity. Some alloys, though, are going to be softer than the component metal. And that's when we do substitutional, but instead of replacing it with a smaller atom, it's with a much larger atom. So in this case, we have a giant bismuth that's going to soften the metal and lower its melting point because it's destabilizing the structure. So I'm going to pause the video and figure out which of these structures are substitutional alloys, pure metals, and which ones would be softer than the original metal. So substitutional, we're substituting metals, so that would be A and D. Pure would be B. And then softer would be A. C would be the interstitial alloy, because notice that we have some of the holes filled. Go ahead and pause the video and try this one on your own. Restart when you're done. So first, because some of the holes are filled in, it's going to have a lower malleability. And then we have the same volume, but now if I took the mass of the sample, it should be a greater mass because again, some of the holes are now filled in. So greater mass, same density, same volume should lead to a greater density. So that's why the answer was D. Go ahead and pause the video and try this one on your own. Restart when you're done. So the last one says less polarizable. That's going to be London dispersion forces. So that's not our answer. But because copper atoms are smaller than silver, they're going to interfere more with the displacement of the alloy. So that's our answer for that one. And finally, Lewis dot structures. Like we said before, bond order, we have one is a single bond, and a single bond is just a sigma bond. A bond order of 2 is a double bond. We've got a sigma and a pi bond. And then a bond order of 3 is a triple bond. We got 1 sigma and 2 pi bonds. Triple bonds are going to have the greatest bond energy. They're the strongest, in other words, because they're the shortest. It's going to require the most energy to break. And then single bonds have the weakest bonds or the slowest bond energy, and they're the longest. Go ahead and pause the video and see what you remember about drawing Lewis structures. Restart when you've drawn these 4. So this one has 10 valence electrons. We get the valence electrons from the periodic table. We're going to hook them together that every line is 2 electrons, so that's minus 2. This one needs 6, this one needs 6, so I need 12. 12 minus 8 is 4. I need 4 more than I have. So divided by 2, I need 2 more bonds. Now I can add them as my lone pairs. Always double check that everything has 8. 2, 4, 6, 8, 2, 4, 6, 8, and that you've only used what you started with, no more, no less. 2, 4, 6, 8, 10. The only things that don't need 8 are hydrogen. It only wants 2. Boron and beryllium. Boron and beryllium are super reactive because they don't get 8 generally. Boron will usually get 6 electrons and beryllium 4 electrons. So in 2O, you should have gotten 16 valence electrons. O was in the middle with 2 nitrogens coming off. We had 12 left, 6, 4, and 6 needed, so we needed 16. 16 minus 12 is 4 divided by 2. We again need 2 more bonds, so we're going to make that symmetrical. And now we can add our lone pairs. So that was your structure for it. NO3 -1 has 24 valence electrons. We needed 18 plus another 2 for nitrogen, so we need 20, but we have 18, so we're 2 short. 2 divided by 2, we need 1 more line. We can add that to any of these. This one has a charge. So I forgot to explain it a second ago, but nitrogen has 5. Each oxygen has 6 times 3 is 18. And because we have a -1, we're going to add 1 to it. That's how we got 24 over here. When it has a charge, you need to bracket the entire ion and put a -1 on the outside, or whatever the charge is. So same thing for carbonate. We had 24 valence electrons. So we should have a very similar structure. So that's what you should have gotten for carbonate. So this one, you first need to add up your valence electrons. So go ahead and add up how many valence electrons each element has and restart when you have that. So you should have gotten 30 valence electrons. Next, I need to connect all the atoms. So I'm going to draw a single bond between each of them. So that's 2, 4, 6, 8, 10, 12, 14, 16. So I have 14 electrons still to use. I need 2, 4, 6, 8, 10, 12, 14, 16. So I need 16. I only have 14, so I need a double bond somewhere. I could put the double bond over here or over here, but my formal charge would be not the lowest possible. We'll be talking about formal charge in a second. But again, you could have put the double bond in any of these 3 spots. After I have my double bond, I'm going to add my electrons. And especially on one like this, you want to double check that you used all 30, no more, no less. So if I add these all up, I get 30. All right, our last type of Lewis structure is acids. So go ahead and add up your valence and restart. So you should have gotten 32 valence electrons. For acids, your hydrogen always comes off of oxygen. So that means P has to go in the middle with my oxygens coming off of the P. Then, since I have 3 hydrogens, 3 of my oxygens are going to get a hydrogen on it. So that's my basic structure. So I've used 2, 4, 6, 8, 10, 12, 14 electrons. So I have 18 left. I need 2, 4, 6, 8, 10, 12, 14, 16, 18, so it works out perfectly. Resonance is when one molecule has a hybrid of Lewis structures. So the true structure is a hybrid of all the Lewis structures that we could draw of it. Super important, the strength and bond length of all the bonds are the same. So let's look back at our structures that we drew a few minutes ago. Of these, this one has a triple bond, but there was only one place I could put that triple bond. So that does not have resonance. This one, I had 2 double bonds, but I'm not going to do a triple single. So again, this one doesn't have resonance. But NO3, I didn't have to put the double bond here. I could have put the double bond here. I could have put the double bond over here. So NO3 has resonance. Carbonate, also, I didn't have to put the double bond here. I could have put it in either spot. So the way that the question was worded, I didn't have to show all resonance structures. But if I did, we'll look at carbonate. You would draw the Lewis structure for carbonate. And then you would have a double-headed arrow, and then you just draw it where the double bond could have been. So in this case, since there was 3 spots that double bond could have been, I'm going to draw carbonate 3 times. Ran out of room a little bit there, but I have my carbonate 3 places. So remember that we set up above, the bond lengths are all the same. So even though it looks like I have 1 double bond and 2 single bonds, so I should have 1 short bond, 2 long bonds, that double bond is actually spread between all 3 bonds, making it like 1 1/3 bond lengths. So all the bond lengths will be shorter than a single bond, but longer than a double bond. And again, strength-wise, they'll be stronger than a single bond, but weaker than a double bond. For this one, go ahead and pause the video and draw ozone. If ozone has resonance, include all valid Lewis structures like we showed a second ago. So ozone has 18 valence electrons. So you should have drawn it like this. Notice I only needed 1 double bond, so I got a lone pair on the central atom. And in this case, I only have 2 resonance structures. So the bond order would be 1.5. So between a single and a double bond. We calculate formal charge to figure out which Lewis structure is a better Lewis structure. So if it says which is a better structure based on formal charge, you'll need to calculate the formal charge of each element to answer the question. To calculate formal charge, you're going to use the number of electrons it came in with. So oxygen comes in with 6 valence electrons, minus how many it currently has. It has 1, 2, 3, 4, and then it gets half of each bond, so that's 5, 6. So this oxygen has a formal charge of 0. Carbon came in with 4, minus, it has 1, 2, 3, 4, so it also has a formal charge of 0. And this oxygen came in with 6, minus 1, 2, 3, 4, 5, 6, is a 0. Over here in B, oxygen came in with 6 minus 1, 2, 3, 4, 5, 6, 7. So that's a -1. Carbon came in with 4 minus 1, 2, 3, 4 is a 0. And oxygen came in with 6 minus 1, 2, 3, 4, 5 is a +1. The formal charges have to add up to 0. So -1, 0, and +1 does add up to 0, and A, they were all 0. We want the lowest possible formal charges. Therefore, A is the correct answer. And our reason would be structure A because the formal charges are all 0, which is smaller than the structure on B. And again, we have all of our work to prove that. If the formal charge can't all be 0, then we want the more electronegative element to be the negative. So out of carbon and oxygen, oxygen would have to have a negative, not carbon. So let's look at one more of these. You are figuring out which of these is the best structure for XeO2F2 and justifying in terms of formal charge. So calculate the formal charge of each element, restart when you are done. So you should have gotten 0 for each of these elements. This one was also a 0, 0, 0. This oxygen came in with 6, but it currently has 7, so that's a -1. Xenon came in with 8 minus 1, 2, 3, 4, 5, 6, 7. So that's a +1. And over here, fluorine is a 0, 0. This oxygen is 6 minus 7, so -1. 6 minus 7, so -1. And xenon is 8 minus 1, 2, 3, 4, 5, 6, so +2. So of these, A would be the best structure because its formal charges are lower. You need to know your electron pair geometries shapes and bond angles. So on here, linear is going to have bond angles of around 180 degrees. So 2 atoms, no lone pairs on central atom. Trigonal planar has 3 things coming off. If it's 3 atoms, it's going to be exactly 120. If one of those is a lone pair, then it's going to be a little bit less, so that's about 118. So the lone pair repels more, causing the bond angle to go down some. Tetrahedral, we say, is 109.5. So that's 1, 2, 3, 4. So this one's 109.5. One lone pair is trigonal pyramidal, and that's 107. And this bent is 104.5. Trigonal bipyramidal has this center, which is trigonal planar, so it has 120 degrees bond angles, but it also has top to side and bottom to side, so it also has 90-degree bond angles. For seesaw, it's going to be a little less than 120, but the bond angles will be pretty similar to 120 and 90 for all of these. T-shape is only going to be 90 because it's a T, and linear will just be 180. And then octahedral, we've got a square in the center, so that's why it's square planar when you have 2 lone pairs. And then to the top and to the bottom, so this is 90 degrees. For this one, your hybridizations, these are going to be sp. These have 3 orbitals, so that's sp2, and tetrahedral is going to be sp3. The AP test won't ask about expanded octet hybridization, so you just need to know sp, sp2, and sp3. As far as polar and nonpolar, if it has a lone pair, then it's going to be polar. That has an exception, though. If it's linear, then that's going to be nonpolar because those lone pairs are in a separate plane. That's also the same for the square planar. And just in case you see the linear of 4 lone pairs and 2 atoms, that also would be in a separate plane, so it would be nonpolar. So those 3, although they have lone pairs, would be nonpolar. The rest of them, if they have lone pairs, would be polar. So go ahead and pause the video and fill in these. As it says on the top, make sure you fill in any missing lone pairs before answering the questions. So before answering the questions, you should have said that nitrogen only has 3 bonds coming off of it, so it only has 6 electrons, so it needs a lone pair on it. Carbon and hydrogens are good, so we just needed to add 1 lone pair. So this nitrogen has 3 bonds and 1 lone pair, so that's trigonal pyramidal as the shape. And so our bond angle should be about 107 degrees. Hybridization, we have 4 things coming off, so that's sp3. S is 1, P is 3, so that's 4 things. So that's how we know it's sp3. Go ahead and pause the video, again, filling in any lone pairs that are needed before solving. So the only lone pairs needed were on oxygen. And so for carbon, we have 3 things coming off. It doesn't matter that that's a lone pair. We still have 3 atoms or 3 bonding sites. So that's going to be trigonal planar. That bond angle is 120 degrees, and the hybridization is sp2. So all of the atoms, the carbon, the oxygen, and the hydrogen, and this carbon are all in the same plane because it's planar. While over here, this nitrogen, hydrogen, hydrogen, and carbon, because it's trigonal pyramidal, are not in the same plane. Go ahead and pause the video, draw the Lewis dot structures for these 2, and then figure out the shape, bond angle, and is the molecule polar or not. Restart when you're done. You should have had 22 valence electrons. So Br's in the middle. And on this one, we have extra electrons. Extra electrons go on central atom. Don't forget your brackets and charge. So 2 atoms and 3 lone pairs is going to be linear because all the lone pairs will be in the central axis. So linear is 180 degrees. And again, because the lone pairs are in a different axis, that's going to be nonpolar. This one had 34 electrons. So we have selenium and we have our 4 chlorines coming off. This one also has extra electrons, but it only had 1 set of extra electrons. So 4 atoms, 1 lone pair is going to make it a seesaw shape. That has bond angles of 120 and 90, or slightly less than 120 and 90. And that lone pair is going to distort it, making it polar.